here. Let's begin. We have completed heat and thermodynamics and radiation in the last lecture. We looked at the last part of spectral emissive power concept and the distribution of black body radiation over electromagnetic spectrum, including the Wien's displacement law and the principle of that ultraviolet catastrophe. That is actually the simple and very formula-based type of part of heat and thermodynamics and radiation in particular. More technical and more important from your JEE point of view from radiation was the application of Stephen's law of radiation and the special case of Newton's law of cooling with the approximation method and that exponential decay of temperature slowly with respect to time and all that. So make sure you revise all those things and also do a revision of the earlier part of heat and thermodynamics, first law and its applications, heat engines, and going back even before that to kinetic theory of gases and all that, because you have a test coming up on Sunday, which will have the entire heat and thermodynamics portion from this track of physics. And of course, the big chapter of rotational mechanics. So that itself is going to be challenging. We also have an additional doubts and discussion session this week. If I remember correctly, it's on Friday morning. So especially anything to do with heat and thermodynamics, you can discuss with me on Friday morning. In fact, you can keep sending me the questions over WhatsApp or Discord or whatever. I will give some hints and try to resolve it. And if we require to solve the entire problem, then we can do it on Friday morning. Or we can do some practice questions on Friday morning, depending on how things go. So today, actually, let's move ahead with the next section of the syllabus, which will be for us fluid mechanics. So again, it's a very interesting and comparatively less technical, easier type of chapter compared to what you studied in mechanics till now. But at the same time, very scoring chapter in terms of JEE. Okay, enough weightage and quite easy to make sure that you can get the questions correct at the JEE Advanced level. So let's begin. Okay. So this will be our first session of fluid mechanics today. And as I said that I know you're preparing heat and thermodynamics, and particularly for the radiation part, you might be having some doubts and questions pending both from the module as well as HC Verma. So we have the additional session on Friday. We will discuss questions and doubts in that. Okay. Keep sending me your questions on WhatsApp till then. Okay. So as the name suggests, fluid mechanics, we are going to deal with the physics of fluids and particularly the applications of the principles of mechanics, like the basic thing of force and momentum or work energy theorem, etc., but applied in a different way to a system consisting of a fluid. Okay. So that's what fluid mechanics is about. The first section of this chapter will be something called hydrostatics, which, as the name suggests, is to do with the physics of a fluid at static equilibrium or rest. So hydro in Greek meant fluid, not just water, but any fluid. Okay. So hydrostatics is basically the physics of, but in this case, we will make a sort of we will make a qualifying criterion that instead of any and every fluid, we'll be dealing with what we call ideal fluids. So fluid, the physics of an ideal fluid. And I'll explain what an ideal fluid is. Okay. At static equilibrium. Or in simple terms, what we call at rest. So that is the subject of hydrostatics. So first of all, let's understand what is an ideal fluid. Just like in the previous section, we saw an ideal gas is one which agrees with the kinetic model of the ideal gas. And according to the kinetic model, it has all those various properties like Brownian motion and the fact that there's no potential energy stored because of any kind of interatomic or intermolecular bonds, but only kinetic energy and so on and so forth. And from that, we get the equation of state for an ideal gas as PV equal to nRT and its various properties. So like that, we have a definition of an idealization of a fluid. Okay, according to which a fluid is said to be ideal if it has two important properties. One is that it is what we call incompressible. That means the fluid is not compressed, at least not compressed easily due to any variations in change in pressure. So it will have a uniform and constant density, which is independent of pressure. So that is what we mean by the first property of ideal fluids, that it is incompressible. And the second property is that we'll assume an ideal fluid is non-viscous, or in other words, that any type of viscous force is absent. So viscous force, as you might have heard, is the equivalent of friction in fluids, but it is not called friction, it is called viscous or fluid drag force. And like kinetic friction, it is a non-conservative force that opposes relative motion. Okay. So in the case of an ideal fluid, we'll assume that the viscosity of the fluid is negligible. So there is no effect of any kind of non-conservative drag force at all when we are dealing with ideal fluid. So the properties of an ideal fluid. So ideal fluid is a fluid which is incompressible. Okay, that means it has a uniform density which is independent of variations in pressure. And B, it is non-viscous. So the coefficient of viscosity, like you have a coefficient of friction, like that we have a term called coefficient of viscosity is 0. So this is an idealization. Of course, no real fluid will be perfectly ideal. Okay. So real fluids are never perfectly ideal, but many fluids like water, kerosene, etc. are approximately ideal unless subjected to extreme conditions of pressure and temperature. So within reasonable limits of our experimentation, limits of variations in pressure and temperature, we can treat certain types of real fluids like water and kerosene, etc. as nearly ideal, which means that there will be very small variations in density with the variations in pressure. So we can ignore those variations in density because there will be something like typically less than a 1% variation or less than a 0.5% variation. So that can be neglected within the, within the you can say feasible limits of experimental error. And also the viscous forces will be negligible compared to the other forces at play, or the amount of energy dissipated by viscous force will be negligible. Okay. So also here we should understand about viscosity. So viscous forces in a fluid are the non-conservative drag forces, like air drag, for example, you've heard about it. So a cotton wool ball moving through air or dropping through air will have a significant amount of drag force which affects its motion, but like a spherical metallic ball will hardly have any significant drag force compared to its weight. So something like that. Okay. So like that, if we have an object moving through a fluid, like a body falling through water freely under gravity, or an object which is projected but under water under the action of gravity. So depending on the material of that object as well as the material of the liquid, in this case we're talking about water, there may or may not be a significant amount of drag force. So that drag force in the case of liquids is typically called viscosity or viscous force. So viscous forces in a fluid are non-conservative drag forces that oppose relative motion. So in a separate chapter called properties of matter, which we'll do after fluid mechanics, we'll be studying about viscous fluids and the properties of viscosity. But in this chapter of fluid mechanics, we are, remember, even if you don't always explicitly mention in question after question, we will always assume that we are dealing with ideal fluids, that is negligible viscosity and nearly incompressible. Or a perfectly ideal fluid would be exactly non-viscous and perfectly incompressible. Okay. Yeah, Ayush, example of this thing, compressible fluid is, for example, any gaseous fluid is highly compressible. Smoke coming out of a chimney is highly compressible. You can see that as it comes out, as the pressure releases, the density of the smoke rapidly changes. So that's an example of a very highly compressible fluid. Or if we increase the pressure, the density will significantly increase. Okay. But even a more everyday liquid like water and kerosene, etc., exhibits compressibility. But for that, we have to subject it to extreme amounts of pressure. It will not happen for minor variations in pressure. Okay. And Aman, yes, we have something called coefficient of viscosity, which I've already mentioned, and it's usually denoted by the symbol of eta. Eta looks like an N with a longer side. Okay. So just like we use the symbol mu for coefficient of friction, like that, when we come to the chapter of viscosity, you'll see that we use the symbol called eta for coefficient of viscosity. But coefficient of viscosity is not exactly the same like coefficient of friction, because coefficient of friction is dimensionless. It's a unitless, dimensionless physical constant, whereas coefficient of viscosity is having physical dimensions. It's not dimensionless. And in that sense, viscous force is different from frictional force, because the amount of viscous force depends on the amount of relative motion, whereas kinetic friction does not depend on the relative velocity. It just depends on the coefficient of friction, that is the material, and the normal contact force. So when we come to viscosity, we'll see that while viscosity and kinetic friction are both non-conservative forces which act such that they oppose relative motion, but the similarity ends there. The rest, they are quite different in how exactly they work. Okay. Anyhow, so in this chapter, we are not going to be concerned with viscosity. Okay. So that is the definition of an ideal fluid. Okay. Now, when we talk about one of the significant properties of an ideal fluid, which we already talked about, it is density. Okay. So density will be denoted by rho. And as you know, the SI unit for density is kilogram per meter cube, and the CGS unit is grams per cubic centimeter. And you should remember the conversion, that 1 gram per cc is equal to 1000 kg per meter cube. Another term that we'll use often for density or related to density is something called relative density. I'm sure you would have heard of this. Or another name for relative density is specific gravity. It's quite weird why it is called specific gravity, because it's nothing to do with gravity. But anyway, so specific gravity or relative density for any material, it is just defined as a simple ratio of the density of that material with respect to the density of water at 4 degrees C. Okay. And we know that the density of water anywhere at 4 degrees C is 1 gram per cc. So when we express the relative density or specific gravity of any material, we know that the value is equal to its density in gram per cc. So for example, if we say that the relative density for mercury is 13.6, that simply means that the density of mercury is 13.6 gram per cc, or 13,600 kg per meter cube, as I'm sure all of you are aware. Okay. Or another common example is that the relative density of ice is 0.9, which means that the density of ice is 900 kg per meter cube, which is why ice floats on water. Something that we discussed about in heat transfer also, that strange phenomena of anomalous expansion. Okay. The only known substance for which the solid state has a lower density than the liquid phase and therefore it floats in the same material's liquid state. You know that. So density is one important property of any fluid. Okay, and obviously we're dealing with an ideal fluid, so we'll assume that in any body of the fluid which is in static equilibrium or at rest, the density is a homogeneous property, or it is uniform throughout the body of the liquid. Okay. Now, next property of the liquid, next physical property related to the liquid we'll discuss is pressure. Now, pressure is a very interesting property. Okay. How do we measure pressure, or what is the definition of pressure? Anybody can tell?
Force per mass unit area.
Force per unit area. Okay, that's correct. Okay. Force acting perpendicularly per unit area. That is the answer that Ansh has given. So it's a little bit more precise. Okay, we can say it is normal force or perpendicular force per unit area. Achha, can you tell me, is pressure scalar or vector?
Scalar.
Scalar.
It's a scalar, na? But if we are relating it with force, then how come we are saying it's a scalar? Because we know that force is a vector quantity, and area mostly till now what we have studied, area is a scalar quantity, though later we'll say area can also be expressed as a vector. So how come pressure is a scalar quantity?
Because direction is removed, because it is always a force on that area.
But force on that area which has a specific direction with respect to the surface, na, which is normal or perpendicular to the surface. Okay, so that is why now when we define pressure, or let's say when we measure pressure experimentally, we have to calculate the normal force acting on a surface. That means the force acting perpendicular to the tangent to that surface, or perpendicular to the surface itself per unit area. So the moment we are saying it is a force in a specific direction, which is normal or perpendicular to the surface, that means we are talking about a component of a force. So component of a vector is a scalar quantity. So that's one way in which you can justify why pressure is a scalar quantity. But actually in higher physics, where pressure is defined in a slightly more complicated manner with respect to force, you may or may not learn, depending on what branch of engineering you study later, you will learn that that pressure is in fact a tensor quantity. Remember, we had discussed long ago when we are doing vectors, we had discussed that there are quantities which are neither scalars nor vectors, or you can say that scalars and vectors are actually special cases of physical quantities which are called tensors. So all types of physical quantities are tensors, but scalars are particular type of tensors which have no directionality, and vectors are particular types of tensors which have certain directionality, and there are other types of tensors which are neither scalars nor vectors, and pressure is an example of that. Moment of inertia, you might have heard, is also another example of that, because when we write angular momentum is equal to I omega. Okay, so at our level of rotational mechanics or rigid body mechanics, we are always dealing with a situation where the axis of rotation is the same as the axis along which the this thing angular momentum is. So omega and L are along the same vector. Or when we write that torque is equal to I alpha, okay, or torque is equal to rate of change of angular momentum, for example. These are all situations where we always take a case where the axis of rotation is not rotating itself. But when we take something like a gyroscope or a spinning top, we will see in that kind of example, the axis about which the rotation is happening, that itself is spinning. So it leads to a very interesting situation where you can see that angular momentum and angular velocity may not be collinear vectors, which means that moment of inertia cannot be defined as a pure scalar. In fact, it has to be defined as a tensor. But anyway, that goes in a little bit advanced level into physics, so we don't need to bother about that at the 10+2 or JEE level. But you might encounter this aspect at a later stage in engineering, so you should actually be aware of it. Okay, so over here we will define pressure as a scalar. At our level in hydrostatics, we'll define pressure as a scalar. We'll define it as the normal. So normal means perpendicular force per unit area on any surface inside a fluid, or you can say in contact with the fluid. is the pressure applied by the fluid. And whenever we define something as a rate of change, force upon area, or displacement upon time or something, remember there are two types of quantities, average and instantaneous. So accordingly, we say that the average pressure, okay, which is the pressure on a surface of area delta A, let's say, in contact with the fluid. This average pressure will be defined as the normal force acting on it divided by its total area. Okay, so let's say we've got a container which has water or some fluid like that. Okay. And at this stage, the fluid need not be even ideal. It could be a compressible fluid also. It hardly makes any difference, as we are defining the general property of pressure. Now imagine we've got some kind of a surface inside it. Like you might just have a piece of paper which is sort of sunk in it, or you might have, let's say, a tile which you placed inside it. Okay. So if this is having a total area delta A, now actually it's a laminar body that I've considered. So the laminar body, like a tile or a piece of cardboard sheet or something, will be bounded by two surfaces. One surface pointing upwards like this, and the other surface pointing downwards like this. Okay. So if I'm talking about the surface which is pointing upwards, that surface will be experiencing a force into its plane like this, and that normal force is the one we're talking about. If I'm talking about the lower surface, the one which is facing towards the ground, but obliquely like this over here, then it will be experiencing a force in the opposite direction. So this upper surface which I've drawn, which I've shaded, which is actually facing upwards like this, that will experience a normal force into it. Okay. So that total normal force divided by the total area is the average pressure that this surface is experiencing because of the effect of the fluid. Okay. But then we can also define at any point inside the fluid what is the instantaneous pressure. Okay. What is the value of pressure at a point instead of the average pressure? So instantaneous pressure. Now here the term instantaneous is not so much to do with at an instant of time, but it's got to do with at a particular point in space. Okay, because we are understanding pressure with respect to position, not with respect to time. Okay, so instantaneous pressure, or we would better describe it as the value of pressure at a certain point, inside a fluid. So how would we define that? So experimentally, if we are thinking, we would think along these terms that again, inside my body of fluid, I want to measure the pressure, or I want to define the pressure at this particular point, let's say. So what I'll do is I'll place maybe an entire surface there, but I will consider only a small section of that surface. So I'll consider a differential area, dA. So that small differential area will be experiencing a small amount of normal force. Okay, so that instantaneous rate, okay, so the instantaneous pressure or the pressure at a point will be defined as that normal force per unit area acting on a differential area at that given point. So this is nothing but normal force per unit area on a differential area or on a very small area. At the given point. And another way to justify why we can get away by treating pressure like a scalar at this stage is because the value of instantaneous pressure at a point will not depend on the direction in which the force is acting. So in one case, let's say I'm placing that differential area like this. So dA is like this. So the direction of the force it will experience will be like this. But now let's say next what I do is I just place it at an angle like this. It's the same one and at the same location. I've just drawn it on the side. But now it will automatically, the direction of force will change so that it remains normal to the surface. And if we are talking about the same point inside the fluid, the ratio of this force per unit area will remain the same. I can keep turning that small surface by whatever angle I like, but as long as it's a very small surface, the amount of normal force per unit area it will be experiencing at a given point will be the same. So it will be independent of the direction in which the area is oriented, and therefore independent of the direction in which the force is acting, because the force is always acting into the surface normally. And at a given point, the liquid has the property that regardless of how I place the area, whether I place the surface vertically or I place it horizontally facing downwards or I face it horizontally facing upwards, at a given point, the ratio of that normal force per unit area will be constant, independent of direction. And that's why it is a scalar quantity. So pressure is a scalar. So this is how we define pressure at any point inside a fluid, that you place an imaginary surface of at that point of area dA, very small imaginary surface, and it doesn't matter how you orient the surface. The surface could be, the tangent plane could be lying anywhere. It could be vertical, horizontal, in between vertical and horizontal, whatever. But the normal force per unit area acting on that differential surface, that will be equal to the value of pressure at that particular point. So this is a very interesting property that you can see that a fluid has. How a fluid interacts with matter is through pressure. It's very different to, for example, how a rigid body interacts with other matter. So for example, if we keep a solid block on the floor, there is normal contact force because of gravity between them. So the floor will experience some pressure, but we keep another solid body against it and we don't press them together. There is no pressure between these two. Okay. So it's very specific in the case of rigid bodies, whether or not there is pressure involved at a contact surface. But you keep this rigid body inside the fluid, and every surface of the rigid body or every point on the surface, regardless of whether that's lying on a horizontal surface or is lying on a vertical surface or whatever, every point on the surface of that rigid body inside the fluid will be experiencing pressure and therefore force due to pressure. So that is a property that a fluid has, which is different from the states of matter like solid. And when I say fluid in general, it includes gases also, it's liquids and gases. Though next, when we study specifically about pressure gradient, we'll be talking about pressure gradient in an ideal fluid. So that is a liquid which is incompressible and non-viscous. The property of pressure, though, is universal to all fluids. So same reason why we have atmospheric pressure. So when I place a three-dimensional rigid body anywhere in the open space, every point on its surface, regardless of whether I'm considering a vertical surface like this one, or I'm considering a horizontal surface facing the floor, or I'm considering even a curved surface like this one facing upwards like this, every point on the surface is experiencing a normal force into it because of the fluid of air that is around it. Okay, so that is the property of pressure that all fluids have. Okay, so having understood about pressure, now we come to the very important first, you can say mathematical interpretation of pressure, and that is the concept of pressure gradient. Okay. All the properties from this point that we will see of an ideal fluid at rest, whether it is the buoyancy property or Pascal's law or whatever, we'll see it is related to what we are learning next, which is the concept of pressure gradient. Okay. We have seen the term gradient before in work energy, so it's in the same context. Pressure gradient inside an ideal fluid in static equilibrium. Okay. So that's just a very complicated way of saying that how pressure varies with position inside a fluid which is at rest, albeit an ideal fluid. So the term gradient in general, is rate of change with respect to position. So mathematically, in one dimension, the gradient operator is d by dx. But in three dimensions, the gradient operator is this. Okay. Where you know that this gradient operator or del operator is like this. Okay. So for example, earlier in work energy, you studied that internal conservative force is negative gradient of potential energy. Okay, so in 3 dimensions, this becomes like this, that the x component of force is minus del u by del x. The y component of force is negative partial gradient with respect to y, and so on and so forth. So that is the term that we are using here also, gradient. So by pressure gradient in 3D system, we mean del p by del x, del p by del y, or del p by del z. This thing is pressure gradient, or collectively we can call it this. So this is what we mean by pressure gradient. Okay. So now, as all of you know from your experience with everyday life and physics from before, that if we have a fluid which is at rest in the ground frame, okay, or it's in an inertial frame, it is at rest, then the pressure only varies with depth. It does not vary in a horizontal plane. Okay, so out of these 3 operators, only one will have a non-zero value, the vertical one, and the other 2 axes which are lying in a horizontal plane, there won't be any rate of change of pressure. But in this chapter, we will not only study about liquids which are at rest in the inertial frame, but we'll also come to a more interesting case where we are looking at a liquid which is at rest in a non-inertial frame. And there we will see that it can have a gradient in more than one direction. It can have, for example, a horizontal pressure gradient along with a vertical gradient. Hence, it's important that from the beginning, we have the vector notation of gradient. Okay, or we understand that when we're talking about gradient, we're talking about rate of change with respect to position in 3-dimensional XYZ space. Okay. So the easiest and most relatable example of pressure gradient is the case where we have, as I was just telling you, a fluid at rest in the inertial frame or in the ground frame. Okay. So an ideal fluid at rest or in static equilibrium in an inertial frame. So as you all know, in this what happens, the pressure increases with depth by the formula density into G into H, and the pressure doesn't change with horizontal displacement. So any 2 points at the same horizontal level inside the fluid will have the same pressure, but any 2 points which are vertically separated from each other will have a pressure difference such that the lower point will have a higher pressure. So this is what we'll see in case 1. But only we'll do a proper proof of that now. The formula that pressure varies with depth linearly . Okay, so let us look at the setup of the derivation for this. Okay. So let us consider like a cylindrical container, okay, which is at rest in the ground frame, let's say. So ground frame is inherently an inertial frame, or it could be at rest in a moving frame also, as long as it is moving uniformly with respect to ground, that is at constant velocity. Those are the fundamentals that you know from mechanics, the difference between ground frame and inertial frame and inertial and non-inertial frame. So this is at rest, let's say, with respect to ground only. So you know that if I keep some fluid in it, its surface will look flat. And the reason why its surface will be flat in equilibrium will be because the pressure varies only with depth. It does not vary with anything else. However, we are going to prove that and derive that mathematically over here. So what I'm going to do now is I'm going to set up my system of axes such that the y-axis is the vertical axis, okay, and the xz plane is the horizontal plane. So what we are going to show that the pressure variation with the vertical axis is going to be negative because y is pointing upwards. So that means as we go upwards, the pressure should be decreasing, and the pressure variation or pressure gradient for x and z axis should be 0. So how we'll prove that and how we'll demonstrate that is by very simple applications of free body diagram and concept of Newton's laws of motion. Okay. So let's say what we have in the container is an ideal fluid of density, uniform density, of course, rho. Okay. And let's also say our acceleration due to gravity is g. Okay. Now for vertical gradient of pressure, del p by del x, del p by del y, we will consider a volume element, okay, of fluid, which is like this, like the one I'm going to draw here. The volume element itself is like, you can think of any shape, but here I'll take the shape of a very thin disk of fluid, which is of thickness dy, and this area is A. Okay, so I'll just consider any such volume element of fluid that is lying arbitrarily inside the volume of fluid over here. So you have this whole body of fluid which is at rest, and now I'm just considering a small section of it, a small volume element of it. Okay, so this is my volume element for which this thickness is dy. Okay, and it's lying, let's say, such that from the bottom of the container, this surface is at a y coordinate of y, and therefore this surface is at a y coordinate of y plus dy, because the thickness is dy. So when we look at the free body diagram next of this volume element, okay, it's free body diagram with vertical forces shown only considering the vertical forces shown. That will next look like this, that I'm drawing a sort of magnified version of that volume element. That thin disk of liquid it has what all forces acting on it. The fluid from below will be applying some force due to pressure. Okay, so let's write that force as dF. So that will be P into A. Okay, or let's write that as F only. Okay, so this is P is equal to the pressure, the fluid pressure, that is at y equal to y. Okay, so then the force that is acting from above on the upper surface downwards, that will become, let's say, some F prime, which will become P plus dP into A, because we are assuming that the pressure is varying with the y coordinates. So P plus dP is equal to the pressure at y equal to y plus dy. So obviously that dP will be a negative quantity because we know that pressure decreases. Okay, so where we'll understand that this change in pressure dP is the vertical pressure gradient del P by del y into dy. Okay, because in general here we'll see that whenever we go through a displacement ds, the change in pressure dP should be equal to gradient of pressure dot product with ds. So it should be equal to del P by del x into dx plus del P by del y into dy plus del P by del z into dz. Okay, so this should be the change in pressure when we go through a displacement of ds, because we are assuming that pressure is a function of x, y, z, suppose, okay, and ds is a general displacement. So in general, if I make a displacement which has all three components, okay, then the change in pressure should be here. But in this case, as I'm going from the lower surface to the upper surface, I'm only making a vertical displacement. Okay, so this is the change in pressure when the vertical coordinate is changing from y to y plus dy. So this dp, it is the change in pressure due to a vertical displacement of dy. So that's why we have to write it like this. Okay, and the third force that is acting on this is of course the weight of this element, which we can write as dm into g. So dm is going to be the density into the volume. So that is density into area into thickness. Okay, so this is the mass of the volume element. Okay, so by now you must have guessed what's happening. We are going to balance these three forces because this is in equilibrium. This is in vertical equilibrium, so the vertical forces are balanced. So you will understand that the force from below F has to be greater than the force due to pressure from above, which means that the pressure has to decrease as we go. dP should be a negative quantity. So that is what will ultimately show us that this vertical pressure gradient del P by del Y is going to be a negative quantity. But it will not only show us that it's a negative quantity, but it will show us its value. We'll ultimately get, on solving this free body diagram, we'll get that the vertical pressure gradient del P by del Y is minus rho G, which means it's a constant because rho is constant. So pressure is going to decrease linearly with height as we go. Okay, so that is what this small derivation shows us here for the vertical pressure gradient. So just note down up to here, and if you finish noting down, then solve the FBD yourself and show that ultimately what we will get here is that the vertical pressure gradient is a uniform negative quantity. So that means the pressure will vary with vertical height y according to this. The pressure will be decreasing as we go up. And this will have a slope of minus rho g. Okay, so this is the result that we'll get from here. Okay, so this is the proper technical way of deriving this simple result. Okay, and why it's important to understand the technical way is because even though this is the simple case where horizontal pressure gradient will be zero, but we will also be exploring cases where that's not happening. The pressure will vary with horizontal coordinate as well as the vertical coordinate. Okay, so it's important to understand this proper vector calculus method of solving this. Okay, so balancing the forces here, you can see that F from this FBD analysis, F has to balance F prime plus this weight. So we get that this change in pressure as we go up through a y coordinate of dy is minus rho g dy. So remember, this change in pressure is given by this relation here. It is the vertical pressure gradient into dy. So that tells me that the vertical pressure gradient is equal to minus rho g. So this is one part of our derivation, and this is the significant part. This is the vertical pressure gradient. Okay, in an ideal fluid, static in an inertial field. Okay, so this is like a universal law from this point for us. Now about the horizontal pressure gradient from here. That is del P by del X or del P by del Y. Sorry, del P by del Z. Okay, we can always consider a volume element which is now like this. Which is having a thickness which is along the x-axis, or we could orient it along the z-axis. Okay. So within that container and the body of fluid, now just consider this volume element. Okay. And as if it is at a x coordinate x for this surface and x coordinate x plus dx for this surface, because its thickness is dx. Now for this volume element, consider the free body diagram with horizontal forces shown. Because we've already understood how the vertical forces are balanced for volume elements in a fluid. So when we consider the horizontal forces, it's very easy to understand here that pressure from both sides has to be equal. Because now the difference in this force, if at all any, should be because of difference in pressure from horizontal gradient. Okay. So here P is equal to pressure at x equal to x. So P plus dP is equal to pressure at x plus dx. So this change in pressure dP is because of a horizontal displacement of dx. So it should be this. Now this is in equilibrium. So you can see that F prime should be equal to F, which means that dP should be 0, which means that the horizontal pressure gradient should be 0. And same way we can show for the Z also, that del P by del X should also be 0. Okay, so this tells us that horizontal pressure gradient del P by del X or del P by del Z will be 0 in the same situation. In a static fluid, in an inertial frame. So once you have established this, now we can see that for this case 1, the pressure gradient in the proper vector notation is just minus rho g j cap. This is, or we can simply say that delta p by delta y is minus rho g, because it's a uniform rate. So, and delta p by delta x and delta p by delta z is 0. So this is a simpler way of writing it, okay? Because it's a uniform rate of change. So average rate of change is equal to instantaneous rate of change. So this is the case that happens in this one, where we have ideal fluid, static in the inertial frame. So what this means is that inside a fluid body, when we consider any 2 points, okay, the difference in pressure for a small displacement is this. So the overall change in pressure between any 2 points will be integration of this pressure gradient from the initial to the final point. Okay. So if I'm going from point A, let's say, which has these coordinates, to the point B, okay, the change in pressure, which will be pressure at B minus pressure at A, will be equal to integration of pressure gradient from A to B. So that will simply result in over here minus rho g dy from A, which means y is equal to y initial, to B, y is equal to y final. Okay, because of this. So this in this equation, this will become minus rho g dy, sorry, minus rho g j cap dot product with a general displacement dx I cap plus dy j cap plus dz k cap. So that is okay. So solving this integration, you can see rho g is out coming outside. So the pressure difference between 2 points is nothing but minus rho g into y of b minus y of b. Or what we understand from this directly, that delta p between any 2 points is nothing but minus rho g into the change in the y coordinate. It does not depend on the change in the x coordinate. So it is independent of x and z coordinates. We compare the pressure at any 2 points A and B. The difference in their pressures only depends on the difference in their y coordinates. But it only depends on the vertical difference between their positions. It does not depend on the horizontal coordinates at all of those 2 points. Okay, so this is a simple takeaway from this. This is what we'll apply in any numerical situation. In any static fluid in an inertial frame, we are comparing any 2 points. The pressure difference will only come from the difference of the y coordinates multiplied by minus rho g. Okay, so now the direct implication of this is that, first of all, when we consider a very straightforward shape of a container, like the cylindrical container that we had considered earlier, okay, and we want to find the pressure at any point inside, in a fluid that is placed inside the container, we want to find the pressure at any point in its volume. We have to just apply this formula. So we have to basically reference that point in terms of its y coordinate with respect to the surface of the fluid. Because if it's an open surface, we know that the pressure at the open surface will be equal to atmospheric pressure. So our reference for pressure becomes the atmospheric pressure, which is at any surface. So this is an open container. Okay, so this one is the open surface of fluid, and this is the ideal fluid of density rho. So now if we consider any point on the surface, we know that the reference point will be that one. It will be atmospheric pressure. Now any other point, we can see that with respect to any point on the surface, all we have to know is the depth at which that point is lying. So if we consider this now, that delta P is minus rho G delta Y, for the Y coordinate being, Y axis being vertical. So now we can see that pressure at B minus pressure at A will be minus rho G into minus H, because the Y coordinate of B is equal to the Y coordinate of A minus H. It's down. Okay. So we can see that the pressure at the point B will be the pressure at the point A plus rho GH, or it will be atmospheric pressure plus rho GH. So this is a simple way of calculating pressure at any point inside this kind of a situation. Okay. So for example, if density is 1 gram per cc, G is, let's say, this much, and the height is 5 meters, and we are taking atmospheric pressure as 1.01 into 10 raised by 5 pascals, then the pressure at the point B will become 1.01 into 10 raised by 5 plus 1000, okay, in kg per meter cube, multiplied by 10 in meters per second square, multiplied by 5 in meters. So in pascals, so you can see it will become 1.51 into 10 raised by 5 pascals. So you can see that typically for a fluid like water, at a depth of 5 meters itself, the pressure is increasing almost by 50% compared to the atmospheric pressure. So you understand that 1 pascal is equal to 1 Newton per meter square, or 1 pascal is also equal to 1 kg per meter cube into 1 meter per second square into 1 meter. So Pascal is the SI unit. Okay. We'll also be talking about the barometric units of pressure like atmosphere, bar, or torr also. Okay. Now the thing is, this is very obvious, but sometimes something that is not so obvious is when we have an odd shaped container, okay, how we apply the concept of pressure at any point inside it in that kind of situation. the difference between absolute pressure and gauge pressure, okay, or what is called hydrostatic pressure. There's a slight difference in these different quantities. So let's understand. When we express the pressure at that point as P naught plus rho gh, which in this case is coming out to be 1.51 into 10 raised power 5 pascals. This pressure that we are getting, this is called the absolute pressure. At the point B. It's like the net pressure. Okay. But we also have the term called hydrostatic pressure. Hydrostatic pressure at a given point, you can think of it like the excess pressure due to the hydrostatic column above it. Okay. So it's like the absolute pressure is equal to atmospheric pressure plus some difference in pressure, where that difference in pressure is rho gh. If you take h as the depth from the open surface. So this delta P over here, this is called the hydrostatic pressure. And it's equal to rho gh, where h is the depth of that point from an open surface. So that hydrostatic pressure is also sometimes called the gauge pressure. Because when we use a pressure gauge, typically a standard pressure gauge is calibrated in such a way that it measures 0 for atmospheric pressure. It only measures the value of pressure which is above and beyond the atmospheric pressure. So that is the difference between gauge pressure or hydrostatic pressure and the absolute pressure. So at the point B, gauge pressure, if we just expressed as this rho gh or 0.50 into 10 raised power 5 pascals. Okay, so hope this point was clear. The difference between gauge pressure and or hydrostatic pressure and absolute pressure. Now, the other thing that is important here is that if we have, for example, a situation where we have, like a pipe which we have twisted like this. Or even we have something like this. And this is sealed, but this is an open. It's open. And these are filled with some liquid. So for example, in this one, if we consider this as the point A, this has some point B, this has some point C, then the values of pressures will just depend on these heights. This height is H1. This height is H2. This height is H3. And we can see that pressure at B will be equal to pressure at A plus rho g H1. Pressure at C will be equal to pressure at A plus rho g H2. Pressure at D will be equal to PA plus rho g H3, where pressure at A will be equal to atmospheric pressure. From this, you can also see that the pressure difference between B and C will be or the pressure difference between C and D like this. Okay. Now, similarly, in this second diagram, if we consider the point on the open surface as A, now we consider a point here as B, a point here as C, and a point just under the sealed surface as D. So if this depth is H1, let's say, and this depth is H2. So again, we will see that pressure at B will be equal to pressure at C because they're at the same horizontal level, and that will be equal to PA plus rho g H1. Okay. Pressure at D will be equal to PA plus rho g H2, where PA will be equal to atmospheric pressure. And therefore, again, when we compare these two, pressure difference between B and C will be 0 because this is 0. But the pressure difference between C and D, or pressure difference between B and C, B and D, will be rho g H1 minus H2. Okay, so in fact, we'll see that this is the working principle of devices like barometers or manometers, which measure atmospheric pressure or pressure in a gas chamber. Okay, so now let us understand two very simple devices that are used to measure pressure based on this principle. So barometer is the first example. So it measures atmospheric pressure. So very basic version of the barometer just consists of an open vessel, like an open beaker, or you can say a wide brimmed container filled with mercury. And then a thin glass tube, which is again open at one end, which is a little bit more than 1 meter long. So what we do is we fill this with mercury completely. So this length is greater than 1 meter. Okay. And then we seal this initially. Sealed at open end. The next step what is done is this is inverted, okay, placed with the sealed end inside the mercury surface, okay, vertically, and then the seal opened. So with the seal closed, okay, we invert this, okay, dip it into this mercury beaker or this container, open container with mercury, and once it is dipped inside, we can open the seal. And also this has to be placed in such a way that the portion that is outside mercury, the portion of the glass tube which is outside mercury, so this was the closed end, that is now here, whereas the open end with the initially with the seal in it was placed inside the mercury surface, and then the seal was opened. And we place it in such a way that precisely 1 meter of the column is outside the mercury level. So this is equal to 1 meter exactly. Okay. So what we observe is that the mercury level drops, okay, leaving behind a vacuum gap. Okay. So this is a vacuum gap, and the level of mercury that remains inside, that we can measure to be X. Okay. So the moment we measure that value X, we can tell that if we compare the pressure at these three different points, A, B, and C, we can see that the pressure at the point A will be 0 because there is a vacuum gap above it. Okay. Pressure at the point B will therefore be equal to pressure at A plus density of mercury into G into whatever that level is. So the absolute pressure at the point B, which is inside the tube but at the same horizontal level as the open surface, so that should be equal to density of mercury into G into X. Whereas C is at an open point, so the pressure at the point C should be equal to atmospheric pressure, and pressure at B should be equal to pressure at C, because the vertical difference between B and C is 0. They are at the same horizontal level. So now relating that, you can see that the atmospheric pressure is equal to density of mercury into G into X. So at sea level, the observed value of X, as you know, is about 76 centimeters. So taking the density of mercury as 13,600 kg per meter cube, the more accurate value of G is 9.8 meters per second square. X at sea level comes out to be 76 centimeters or 0.76 meters. So when you substitute that, the measured value of atmospheric pressure at sea level comes out to be 1.01 into 10 raised by 5 pascals. And this is called 1 atmosphere. The barometric unit is 1 atmosphere. Okay. Or sometimes we also refer to it as 1 bar, a pressure of 1 bar. Okay. Or we also say that it is equivalent to 76 centimeters of mercury. So this is another way of expressing pressure. If pressure is expressed in so many centimeters of mercury, it means that the pressure is equal to density of mercury into G into X. Okay, so this is the simple working principle of barometer, which functions on the principle of vertical pressure gradient. Okay, so this is about the barometer. A manometer works in a very similar fashion, okay, but it measures the pressure inside a gas chamber instead of the open atmospheric pressure. Okay, so there are many different versions of manometers. So one form of a manometer is the basic one which I'm showing. So this is a gas chamber. And we have connected the manometer at a point like this. Okay, so you have something like a U-tube, which is connected to a mercury reservoir, let's say, and from here we have connected the gas chamber. So this is of course assuming that the gas is at a pressure P, which is greater than atmospheric pressure. So what will happen is that the mercury might be like this, whereas part of the gas will, little bit of the gas will leak out because of the excess pressure. So now you can see that we can measure the gas pressure by comparing this point here with this point here with this point here, which is, this is an open surface. And this is a mercury column. So if this level difference is X, you can see that pressure at C is equal to atmospheric pressure. Pressure at B is equal to, therefore, so it is atmospheric pressure plus density of mercury into G into X. Now pressure at the point A is equal to the pressure of the gas. And pressure at E will be equal to pressure at B because they're at the same horizontal level inside mercury. So comparing these equations, you can see that pressure of the gas will become P naught plus density of mercury into G into X. Okay, so there are some variations also of manometers with slightly different structures and how the mercury tubing and all is done. But they all work on the same principle that you can compare 2 points in the mercury column which are at the same horizontal level, and in one you can compare the pressure in terms of atmospheric pressure plus some column pressure because of mercury above it with respect to a reference open surface, and the other point you can compare with respect to the reference pressure of the gas inside. So from that you can get a comparison between the gas pressure and the atmospheric pressure, in terms of density of mercury into G into some height difference. Okay, now the next application example you will see is related to like hydrostatic pressure concept or gauge pressure concept. Is an example relating to the net force on any surface inside a fluid due to pressure. So the idea is that the net force is calculated by integrating pressure over area. This idea like this, okay. And why I'm showing this as a scalar equation is because the force is already decided in direction. This net force will be normal to the surface. Okay. So let's look at a numerical example of the application of this. So we have an open cubical container. You have dimensions L by L by L, let's say. And it's filled right up to the brim with an ideal fluid of density rho. So it has 5 of its surfaces. I mean, all 5 of the surfaces, the 4 side walls and the floor, they're all in contact with the fluid inside. So each of these individual surfaces is experiencing some net force because of hydrostatic pressure. Okay. So we have to calculate the net force on each of the surfaces. So this is an open cubical container. Dimension L by L by L. Filled with an ideal fluid of density rho. Okay, filled to the top, as you can see. So we want to find the net force due to hydrostatic pressure on the floor of the container. Is very easy because there's a uniform pressure, and any of the side walls, which is a little bit more complicated because there's variable pressure. Pressure varies with depth. So we have to use this integration method. Okay, so by now you've seen quite a few examples of application of definite integration and surface and volume integrations, etc. So you should be able to figure this out quite easily. Just try this out, we'll discuss. So for the side wall part, you'll have to use the integration, and you should take an area element such that you keep into consideration that the pressure is varying with depth. It is not varying with horizontal coordinate, it's varying with vertical coordinate. So you should accordingly select your differential area dA and do the integration. So express the pressure as a function of the depth, right? And then take a suitable area element and do the integration so that you cover the entire side wall, which will be having a total area of L into L. And remember, we are calculating the net force due to hydrostatic pressure. So don't consider the absolute pressure at a point. Okay? Consider the hydrostatic pressure at a point because of the fluid. Yes, that's correct, Nikita, Naman. Very good. So for the first part, you can see that if we consider the floor, we don't have to do any integration because the pressure is uniform. So you consider any small area, the normal force acting on it will be that uniform pressure into area, where that uniform hydrostatic pressure is rho GL. So the net force will just become pressure into area for this surface. So the net force acting on this surface will become like this. So you notice that is in fact equal to the weight of the liquid. This rho GL cube is actually, it's equals to the weight of the fluid body. Okay. But when we come to the side wall, so let's consider any one side wall. So let's say this side wall, this one, considering side wall 1. So as the pressure is varying with depth, the convenient thing to do would be to take a horizontal thin strip as my differential area. So at a depth of y, if I take a thin strip of thickness dy, then the force acting on that thin strip will become rho gy into L dy. So pressure varies with depth. Hydrostatic pressure, remember, it's not the absolute pressure. And area of that strip is L dy. So now this is experiencing a net force, say F net prime. So that F net prime will just become integration of this df and also if you see the force profile from the side, see the side view, because pressure varies with depth. So at a depth of y, so you can also see it as an interpretation. This is like an average pressure into area. So you can see that this pressure equal to rho gy, it is a linear function. So its average value therefore P average will be like arithmetic mean. So there's an easy way to remember this result also. Okay. Now another interesting fact about this situation here is if we calculate the, before we come to that fact, if we consider the water body or the fluid body as an object and think of its free body diagram, you will see that on that water body, or on that fluid, there is like a normal contact force that the floor is applying. So that is equal to that this much. Okay. And each of the side walls is now applying some normal reaction, let's say N1, which cancels off in pairs like this. So the net force because of the side walls is 0. So each side walls applies that force we calculated as F net prime. Okay. But the net force due to the 4 walls on the water body is 0. It's a vector quantity. Okay. So ultimately the weight of the fluid body is balanced by this normal contact force. That's one important thing to realize. And the other thing is we can also consider the concept of torque due to force on side walls. Okay. And from that, the center of force, like your center of gravity or center of mass, or later we'll study center of buoyancy also, like that there's a center of force for this net force that acts on each of it. Okay. So if we again consider that first wall, you will see that there is some net torque that we can consider about this axis, or there's a net torque that we can consider about this lower axis also because of these forces. So we want to calculate that net torque. We can come up with an integration method. Okay. So we want to find the net torque on the side wall about its axis, or about an axis which is at its upper edge. Okay. At its upper horizontal edge, like the dotted axis that I've shown here. So about this axis, I want to consider the net torque.
ऐसे नहीं करते गंदी बच्ची.
Okay, so how we'll calculate this? This will also have to be
तुम्हें
calculated by integration. So if we take the side view of that wall, then we are considering this as the axis. So on a small element like this of thickness dy at a depth of y, there's a force df like this, which is pda. So that is creating a torque like this. That is equal to that force into the moment arm. So that is pressure into area into moment arm. So that is rho gy into L dy multiplied by this moment arm. So on that differential element, the amount of torque acting is rho gl into y squared dy, about this. So again, seeing in the 3-dimensional picture, if I consider that thin strip at a depth of y, because of the net force acting on that thin strip due to pressure, this force is creating about this axis. It's creating a torque, which I've shown. this is creating a differential torque like this. So the net torque, we have to integrate this. Yes. So Kevin, can you calculate the torque also now? I think you've given the answer for the force, no? Yes, very good, Javel, that's correct. So you'll see that the net torque about that particular axis that I've considered, that will be rho GL y square dy integrated from y equal to 0 to y equal to L. So that will be rho Gy L to the power 4 by 3. So the torque is like this. In magnitude. Okay. Now you can also see that this torque is like a force into some kind of momentum, where that net force was rho G L cube by 2. So this is like rho G L cube by 2 into L by 6. Sorry, into 2L by 3. So that means the center of force will be from the top edge. It will be at a depth of 2L by 3. So obviously it will act along this symmetry axis, which is dividing this in L by 2 and L by 2. But it will also act through a point like this over here. So this C is now the center of the force, which is at a depth of 2L by 3. And you can understand why the depth is more than L by 2, because the pressure increases as you go down. So the center of force, the force is more concentrated on the lower part of the wall compared to the upper part. So it is like the effective point through which that force acts.
So the torque will be 1/3 rho g L raised to 4, right?
Yes, 1/3 rho g, sorry, not y. Yeah, my mistake. This y is not there. It's actually y to the power 3 by 3, which we have integrated from 0 to L. So it is rho g L to the power 4 divided by 3, correct? You can think of this like the net force into the y coordinate of the center of force. This is the y position of the center of force with respect to this. Okay, so hope this is clear to all of you. Yes. So we'll conclude the session here with this today. Okay. Next time we will see more properties of ideal fluids from this concept of pressure gradient, including the property of Pascal's law, which is based on the fact that pressure changes are transmitted equally to all points inside a fluid. And based on Pascal's law, you have devices like hydraulic lifts, etc., that are built, taking advantage of the property of pressure gradient and Pascal's law. And we'll also look at Archimedes' principle and the concept of buoyant force. And of course, we will look at situations where horizontal pressure gradients can also act, because we might be having a fluid which is at rest in an accelerated frame or in a non-inertial frame. So these are some of the things we'll be looking up in the next lecture. That's it for today. Thank you, people. Friday morning, we have the doubts and discussion session for this thing, heat and thermodynamics. So any questions and things that you want to discuss, please keep them ready for that.